Folks, how we doing? Welcome to our last video lesson for Chapter 7. Today we are going to be talking about our last special types of quadrilaterals. Our focus for today is going to be on what are called trapezoids and kites. So we've just got done in our previous section talking about parallelograms and the special types such as rhombuses, rectangles, and squares. So trapezoids are going to be very similar to a parallelogram. However, parallelogram meant that opposite sides were always parallel to each other. And we also talked about how that opposite sides were equal, opposite angles were equal. So in a trapezoid, instead of having two sets of parallel lines, we are only going to have one pair of parallel lines. So that's the big difference here between a trapezoid and a parallelogram. So what we call the parallel sides here, you'll notice that B to C marked with that arrow would be parallel A to D. So those two sides would be parallel. The two sides that are parallel to each other, we call them the bases. And then we have two sides, A to B here and D to C, that are not parallel. You would notice that if we were to extend those lines beyond, they would eventually intersect up here. Those two sides are what are called the legs. And then we are going to be looking at some special relationships in terms of the angles formed on the inside. So it's a little bit different because we have two bases, the two parallel lines. We do have some base angles up here between B and C. And we do have some base angles down here between A and D. And we're going to look at those things. One of the special types of trapezoids, however, because obviously we have a quadrilateral with opposite sides parallel. So the one time in which you would have a special type of trapezoid is what's called an isosceles trapezoid. One of my favorite math words of all time. Isosceles means that the opposite sides are going to be equal. In this case, the legs. So if I were to have, let's say, two parallel lines here where one is going to be larger than the other. Okay, a trapezoid is going to have where your opposite sides, the two legs, are going to be equal in length. Okay, so think of this, if this were A, B, C, and D, that is A to B and C to D would be equal. So we are going to be looking at some special relationships within isosceles trapezoids. So our first example is just to be able to identify within a problem, do we have a trapezoid to start, and is it isosceles? And then we're going to make use of that isosceles trapezoid idea. So you're given 4 points here, A, B, C, and D. We're going to plot those to form a quadrilateral, and then I want to know, is it a trapezoid and is it isosceles? All right, so first thing, we have A, B, C, and D drawn here. So in order to start off, in order to be a trapezoid, what we need is that opposite sides are going to be a parallel. We're going to need one pair of opposite sides being parallel. So when you look at this, parallel means that they're going in the same direction. They will never intersect. So we can see right away, A to B goes side to side. It's horizontal. D to C is also horizontal. So I know that this is going to be a trapezoid at the very least because I have a pair of parallel lines. But we can tell that A to D and B to C, however, are not parallel. They would eventually intersect down here somewhere. Okay? Now, in order to be an isosceles trapezoid, isosceles means that the two legs, A to D and B to C, should be equal to each other. So that's what we're going to figure out, are they equal? So to do that, let's use that idea of slope again. Let's see, instead of trying to find the distance of that line that goes in, or side that goes in an angle, let's look at the slope. So if I look at the slope from A to D, I would be going down and right. So I would go down 6 boxes and right 2. Sorry. So that means my slope would be -6/2. Now notice that C to B goes in the opposite direction. Instead of going down, it goes up. But we want to identify, does it go up and right the same distance? So here it would go up 6 and right 2. So this would have a slope of 6/2. So ignoring the sign here, I know that this one goes down and this one goes up. Notice that I get the same slope for each of them. So that means, yes, this would also be an isosceles trapezoid because not only do I have a pair of opposite sides, but the I have a pair of parallel opposite sides, but my non-parallel opposite sides, A and D, called the legs, that those two things are equal in length. All right, next example, we're going to do a similar thing, except now we're going to try and see if we understand this idea of an isosceles trapezoid, and I want you to find the missing point. So you're given A, B, and C, and our goal is to figure out where would D need to be in order to have an isosceles trapezoid. So let's start off first by plotting those points. All right, so here's what we have so far. So I have A and B and C. All right, so this one's just a little bit different order. So here's A, B, and then C would be here. So I'm going to connect A and C, and I want to know where would D need to be in order for me to have an isosceles trapezoid. So real quick again, I need to have opposite sides parallel to each other. So the best way to do is here I have A to B, which is it's horizontal going left to right. So that means from C, I would need to draw another line going left to right so that it's parallel. But the point is where do I stop this line that I'm drawing? So again, in order for it to be an isosceles trapezoid, the opposite sides, the legs, need to be equal in length. So the way to think about this is, think about like we did in the previous problem. What is the slope of A to C? A to C would go up 4 and over 4. Okay, so that would be a slope of 4 over 4. So what I want to do is I want to do the same thing from B. I'm going to go up 4 and over 4, and that should put me right here at this point of 4, 0. So then if I were to connect that again, that is a terribly drawn line. But if I were to connect that right there, I know that this slope, ignoring that it goes left, is up 4 and over 4. So that would be point D then in this case would be at a point of 4, 0 in order for me to have an isosceles trapezoid. So these first two examples just using our idea of trapezoids and isosceles trapezoids to try and find these points. All right, next thing, what are some special properties of these trapezoids? So because we have two parallel lines, we cannot specifically say that obviously the opposite sides are equal, right? In isosceles trapezoid, we do know that these opposite sides are equal. So the best thing that we can look at within an isosceles trapezoid is what are called the base angles. This is what's called the base angles theorem. So what the base angles theorem states is that the base angles are always going to be equal to each other, okay, as long as they are on the same base. So notice A and D are on this bottom base. So I would say that A and D are equal to each other, and then B and C are equal to each other because they're on that base. All right, so we have two congruent angles, but those angles are going to fall on the same base. All right. So what we're going to use is we're going to use this idea to try and find some missing angles. So in this diagram, you are given a isosceles trapezoid, J, K, L, and M. You're given one of the angles, which in this case is 85 degrees, and our goal is to find the rest of the angles. So here's what I know. Again, the base angles theorem states is that 85 degrees is one of the base angles for the base of K to L, so that the other base angle on that same side, which would be angle K, should have the same measure. So I know here that angle K should equal 85 degrees. Okay? Now the question is how do I find these other two angles J and M? What I do know is that angle J and angle M should be equal to each other. Okay? So the idea is this, if you remember, that all quadrilaterals, again, will add up to 360 degrees, all their internal angles. So what I have here are two angles already, both 85 degrees, and I want to figure out what these two are. So the best way to do this is to think about this. If I have two angles that are 85, if I were to add those two angles up, 85 and 85, that would give me 170 degrees. Okay? Now, the total, all four of them have to add up to 360. So let's think about, if I already have 170 degrees and I take that away from 360, how many degrees do I have remaining? And I would have about 190 degrees remaining. So that means these two angles, J to M, should add up to 190 degrees. Now, since J and M are both equal, here's what I'm going to do. I'm going to take 190 and divide it by 2. I'm going to cut it in half because if J and M are both the same, they both have an equal part of that 190 degrees. So if I take 190 divided by 2, you're going to get 95 degrees for both of those. So that means angle J is going to be 95 degrees and angle M is going to be 95 degrees. Okay? So that's using the base angles theorem, knowing that the angles on the same base are always going to be equal. All right, so what I want you guys to do is try example 2B here. So example 2B, you are given angle A, which is 42 degrees, and your goal is to find the missing angles. Think about what we did in example A. So why don't you guys try this one on your own. All right, following the same route that we did in example A, I know that then angle B, or angle D, I'm sorry, would be 42 degrees. So then what I did is I took the two 42s, added them together at 84, take them away from 360, which is always the total inside a quadrilateral. You get 276, and then I took that and cut it in half to figure out how much each of these angles would be, which would be 138 degrees. So again, using the base angles theorems of isosceles trapezoids. All right, next special thing we're going to talk about with the trapezoid is what's called a mid-segment. Now, a mid-segment is actually something we did back in Chapter 6 with a triangle. To draw a mid-segment of any sort of shape, what you're going to do is you're going to find the midpoint of the two sides across from each other and connect them. So let's say I found the midpoint of my leg and the midpoint of the other leg. So here we're going to find always the midpoints of the legs. The mid-segment would be the line that connects those two midpoints. So here's what I know if it's a mid-segment, that again it's cutting, being that a midpoint is going to cut the two legs in half. What we're going to do is we're going to look at the relationship here between this mid-segment and the bases. So what it says here is that the mid-segment is going to be half the length of the sum of the two bases, okay? Or you can think of it as like a middle value. So for example, let's say that this length right here was 20 and this length right here was 10. The mid-segment is going to be half the distance between 20 and 10. Now, the best way to find that is if you take 20 and 10 and add them together, you're going to get 30. Okay, so that's the sum of the two bases. The mid-segment is going to be half of that length. So I would take 30 and divide it by 2, and I'd get 15. So my mid-segment length would be 15. Now, why I say it's the halfway points, think about this. The distance between 20 and 10 is 10 units. So if I take 10 from the small and add 5, I would get 15. And if I add 5 again, I would get 20. So it's the middle distance or middle length that's halfway between 20 and 10. So two ways to think about it. You can actually think through what the length would be, or here the mathematical approach is to add the two bases and divide by 2. It's called the mid-segment of a trapezoid. All right, so our goal is to use the mid-segment here to try and solve. So in example A, you're given the lengths of MN, or so you want to find the length of MN, and you are given the lengths of PQ and SR. So what we want to do is the mathematical way to do is we can take the two lengths already given, the longer side and the shorter side of 12, add them together, and that's going to give me 40. And if I take 40 and divide it by 2, that should give me the mid-segment length, which is going to be 20. Yep, and so again, then that 20 inches would be halfway between 12 and 28. So again, just to show that, start at 12. If I add 8, I would get to 20. And if I were to add 8 again, it would get me to 28. So it's halfway between those two lengths. All right, now let's see if we can do the same thing, but now I'm going to give you the mid-segment and the shorter of the two lengths. So I'm giving you here, this is the base, JK, parallel to ML. All right, so here P to N is going to be that mid-segment. So then how do I find ML? Now this is a good way to understand that halfway point. In order to get from 9 to 12, I would add 3. So that means if I follow that pattern, if I add 3 again, that should give me the longer segment. So if I take 12 plus 3, that should give me 15 centimeters. So it's a quick way to do it. If you understand that M to N to P is halfway between, or is the halfway distance of J to K and L to M, you can do it that way. All right, and lastly, let's take a look at example C, even though it says B again, but now we're going to look at this on a graph. So to do this, we'll kind of look at the slope. So it says find the length of the mid-segment. So this one's pretty easy to look at just the slope of what's going on here, but I just want to show this. So if we look at, let's say, S to V, I know that it goes down 2 and over 1 box. So that means its slope would be -2 over 1. I'm going to compare that to the opposite base, which is T to U. So T to U would go down 4 and over 2. So that means down 4 and over 2. So that means our mid-segment has to be half of that, kind of the midpoint or halfway distance of that. So you'll notice here that this segment goes down 3 boxes, and then it goes right 1.5. So I'll just write this here. It goes down 3 and then 1.5. Now I know that kind of looks weird in terms of a fraction, but just to show you guys, okay, here's 2 to 4. Think of 2 to 4. I would have to add 1 to 2 to get to 3 and add 1 from 3 to get to 4. Okay, 3 is the halfway point between 2 and 4. Now this is tricky, but what's the halfway point? How do I get from 1 to 1.5? Well, here I would add 0.5 to get to 1.5, and then I would add 0.5 again to get to 2. So that halfway point would be 1.5. So I can view this on a graph. It follows the same kind of pattern, but again, we can use that principle of slope. So this is dealing with what's called the mid-segment of a trapezoid. Okay, baby shawties, last one here. We're going to look at what's called a kite. You guys are probably familiar with this. It's the last special type of quadrilateral. We don't have any sort of parallel sides, but what we do have within a kite is it has 2 sides, or 2 consecutive sides. Okay, so the word consecutive means in a row. So think of like A to B and B to C would be consecutive, B to C, C to D would be consecutive, C to D, D to A would be consecutive, and so on and so on. So here we have consecutive sides are going to be congruent. Different than a parallelogram where we had opposite sides being congruent. Same thing with a trapezoid. So we have consecutive sides being congruent. So you'll notice here that A to B would be congruent from B to C. And then the last 2 remaining sides, C to D, would also need to be congruent. That makes a kite, okay? All right, so what we're going to do is we're going to look at some special properties of kites. So we're going to look at what's called the diagonals theorem of kites and then the opposite angles theorem of kites. So with the diagonals theorem of a kite, the diagonals, again, are any two, or a line that connects any 2 points across from each other. So you have C to A, and then you have B to D. So what it says here is that these 2 diagonals drawn here are always going to be perpendicular to each other. Perpendicular, again, means that they are going to intersect each other at 90 degrees. All right, so the diagonals are always going to be perpendicular. And then lastly, the angles here, it says that 1 pair of opposite angles are going to be equal. So in this case, it is going to be the angles between the 2 non-congruent sides. So we have B to C and C to D, that this angle would be equal to the one across from it. So again, that's what the word opposite means, is that those 2 angles across from each other would be equal, but that does not mean that D to B will certainly be, or not be equal. It's only 1 pair of opposite sides that's going to be equal inside of a kite. So our goal is to use this idea of properties of kites to try and solve for things. So mainly here in these first 2 examples, we're going to look at the whole idea of the opposite angles. So in this case, you're given 2 angles, 48 and 101, and our goal is to find angles 1 and 2. So in a kite, that the angles across from each other, angle 1 and angle 2, are going to be congruent. And again, it's the angles that are between the non-congruent sides. So this side is smaller than this one, so we're looking at angle 1, comparing that to angle 2. What I know here is that angle 1 needs to equal angle 2. So if I'm given 2 of the angles already, 101 and 48, again, I can add those 2 things together, which would give me 149 degrees. And then always remember that in a quadrilateral, all the angles add up to 360. So if I were to take 149 and take it away from 360, I would get 211 degrees. Now the idea here is this, is that angle 1 and angle 2's got to add up to 211. So to find those 2 angles, I'm going to take 211 degrees and I'm going to cut that thing in half, divide it by 2, and that's going to give me not a pretty angle here, but 105.5 degrees. So that means angle 1 and angle 2 would both be 105.5 degrees. So if I were to label that 105.5, and same thing here, 105.5. Not the prettiest answer, but again, those 2 angles are going to be equal. All right, similar idea here in number B. You're given 44 and 80. So again, the opposite angles, angle 1 and angle 2, those are again between the non-congruent sides, are going to be equal to each other. So what we know is, again, that angle 1 is going to equal angle 2. You are given 44 and 80 as our 2 angles so far, so I can take those 2 and add them together, which would give me 124 degrees. I'm going to take that then and subtract it by 360, which is the total for all quadrilaterals, to give me 236, which would be how many degrees are remaining. And then lastly, I'm going to take 236 degrees and divide it by 2, which would give me 118 degrees, which again would be the measure of both angle 1 and angle 2. So they'd both be 118 degrees apiece. Again, so that's using the opposite angles of kites. Last one we're going to look at is the idea of the diagonals. Okay, so real quick, you have the two diagonals drawn here from D to F and from E to G. So the diagonals theorem states that the diagonals are going to be perpendicular to each other, which means that they're going to intersect at 90 degrees. So here you're being told that this angle, 6x plus 6 degrees, is going to be represented here. So here's what I got to know, that 6x plus 6 should equal 90 degrees because all diagonals are going to be perpendicular. So then I could take this equation and solve for x by first subtracting 6 to both sides and getting 6x equals 84, and then lastly dividing both sides by 6, which would give me x equals 14. And again, just to show you, if I take 6 times 14 and then I add 6, I should get 90 degrees. But again, this is using that diagonals are going to be perpendicular to each other. All right, so a lot of meat and potatoes, but this is going to wrap up our chapter here. We talked about, in this last section, trapezoids and kites. Overall, as a grand scheme, all the different types of quadrilaterals that we had, and our goal was looking at some of the special relationships when we had sides being parallel, what that caused, and then with this last section, what happens when the sides are not parallel, what other special relationships we have. So like always, make sure you jot down any questions you have. Good luck on the practice set, and we'll see you guys later. Peace out.